Okie dokie. Chemistry time. Today, as you can tell from what's already on the board, we're talking about matter and its configurations. Matter, write it down please, and its configurations. Let's very carefully move this over to here. There we are. See if we can get the picture-in-picture to go. Oops, I hope that didn't mess everything up. Stand by. I might have messed everything. And its configurations. Okay, that did work. The objective, as you can see, is identify matter based on its properties. I'm going to add to that a little bit. Identify matter based on its properties and describe the atomic nature of matter. Describe matter, its properties, and atomic nature. Or in other words, the configurations of matter. How matter is configured in the universe. Speaking of the universe, what is the whole universe? The observable universe, let's start with that. Let's talk about that's a good place to start. The entire universe. The observable universe. As Faye and I were gently discussing before, there are, or at least there may be, things that are unobservable about the universe. You don't have to agree whether there are or not, but you will have to agree that some people might think there are things about the universe that are unobservable. Okay? But whether you agree with the fact that that's true or not doesn't matter, because science is concerned with the observable universe. That is, the things that we can empirically with our senses or with the magnification of our senses, like a microscope or a telescope, observe about the universe. Science is concerned with the observable. Science does not make claims and is not made to make claims about the unobservable, so we're not talking about that. We're talking about the observable universe. Within the observable universe, what are there? There are two things. Matter. Yeah. Yes. Who said that? Nice job, Wes. Suspiciously nice job, Wes. Matter. And space. Oof. Okay. I agree, Fate. Matter would be meaningless if there wasn't space between matter, right? How can you define the black marker on the whiteboard if there's not white for it to stand out against, right? Put another way, if this were all black and I were writing on it in black, nothing, right? So without space, it is hard for us to define. But I'm going to put that in little here because the phenomenon of space is kind of by its nature unobservable. It's a negation of what could be observed. Will? Energy? Yes, that's what I was looking for. For the record, Faye, I like yours more. Stuff and not stuff, I think, is a cooler dichotomy within the universe than matter and energy. These are not dichotomous. These things work together. But I like that one. Bye. Matter and energy. This will be dealt with in chapter 5 of our text, so we're not going to worry about that right now. We're talking about chapters 3 and 4. So today we're talking about matter. We're just going to zoom in on that. Zoop! And now it's this one. Actually, all year we're talking about matter. The title of this text is Chemistry. I'll just have to spread out. Chemistry, Matter, and Change. Right? So all year long we're talking about chemistry, matter, and change. And those are not three separate things. Chemistry, that is, chemistry is made of matter and its changes. Matter and its configurations. So in the first thing we discussed this year, we talked about what is science in general. And then we moved on to talk about how do we use math and measurements in science. And those are both kind of like building blocks. Like you have to know this before you can do a good job of this. And this is the very basics of chemistry, matter and its configurations. What is matter made of? Well, yeah, we're building a little concept map here. So matter, we're going to say, is atomic. And that's one thing we're going to talk about later on. So hold on to that. Matter is atomic. Matter, another way we can think about matter is that matter is kind of broken down into pure substances or mixtures. Whoops. We could say pure substances or impure substances. I don't want this to be really as opposed to atomic. Let's put its... I was going to say configuration again, but... let's just put basic forms. Mixtures and pure substances. The thing that links pure substances to the atom is what? What kind of pure substance from your vocab and your text is atomic? Atoms represent the smallest particles of the elements. Good. Yep. So that'll link our two things here. So elements are one kind of pure substance. What's another kind of pure substance? Can there be something that's a pure substance that isn't just an element? Hey, I keep looking over here, but what's over here? The camera can't follow me. But what's over here? The periodic table of the elements. So these 118 specific substances are considered elements. Why?
Because they aren't made of anything else.
Yeah. Are they?
You can't separate them from anything.
If you, let's phrase it this way. It's not that you can't break them down. It's that if you do break them down, they're not this element anymore, right? What is bismuth made of? What three kind of things in the universe is bismuth made of? Protons, neutrons, and electrons. What three things are antimony made out of? Antimony atoms. Protons, neutrons, and electrons. Like if we break any of these down, they're no longer that element. So they're the most basic component of an element is the atom. This word atomic, it comes from the Greek word a or a, the Greek letter alpha, tomon, which means cannot or won't or without, but some kind of negation, cannot be cut. It isn't, strictly speaking, we might say in Latin, in sensu strictu, it is not in the strictest sense true. We can break down atoms. But the name of an atom, and the name alone, comes from a man named Democritus in the 4th century BCE. And he basically had a thought experiment that was, here I have some cheese or bread or cake or something. If I cut it in half, it's in half. If I cut those in half, it's a quarter, an eighth, a 16th, etc. Could I get, he thought, probably drunkenly, he was an ancient Greek, probably really low on wine. Could I get to a place where I can no longer break that in half? And just the very fundamental idea of that he called atomos, the atom. Right, to us, the atom sounds like kind of a fancy science word. In Greek, it literally means can't be cut. So he's sitting there sloshed on wine. He's like, what if I couldn't cut anymore? I'll call that can't be cut. Right? It's not really that profound if you know the Greek, but we call it an atom still to this day because he named it that. Does that kind of make sense? So this word atomon means can't be cut, and that's what we still call the atom today, even though, as Faye correctly points out, the atom, we understand, is made of smaller pieces, and it has been and can be broken down, and in fact it continually is broken down in some cases of nuclear radiation, which we'll talk about later. But we still use the name atom to be the most fundamental part of an element. Think about it this way. Even though it can technically be broken, it's no longer that element if it's broken down, right? It changes elements. So the element itself, that's the most basic part of an element. What other kinds of, back to my original question, what other kinds of pure substances are there that are pure but are not on this? Can you think of an example, perhaps, of a pure substance that is not an element? Isotopes are an atom that has different numbers of neutrons in the same atom. So that would still pretty much be an element. I'll give you a hint. There's one. Example, H2O. That's one. I'm going to write it as H2O because, one, you all know this stands for water. And 2, it shows that pure substance, I should have put another bubble in here, sorry. That kind of pure substance is something we call a compound. So it's one or more atoms together form, actually it's more than one atom together forms a compound. Example, H2O. So it's more than one atom bonded together in a certain ratio. That's very important for this, is that it must be a certain ratio. And that ratio is as much what determines what the compound is as what's in it. What's water made out of? It's made of hydrogen and oxygen. What about hydrogen peroxide? I'll write the formula for hydrogen peroxide. BT dub, you should know that the peroxide polyatomic ion is O2, 2 minus, right? That's one of your polyatomic ions. So this is hydrogen peroxide. What's it made of? Yeah, hydrogen and oxygen. It's made of hydrogen and oxygen. What's water made of? Hydrogen and oxygen. What's hydrogen peroxide? Hydrogen and oxygen, right? So these both are made of hydrogen and oxygen. Are they the same thing? Obviously not, right? I shouldn't say obviously, because the point I'm trying to make is that this might not be obvious to you. But if I were to give you a glass of water and a glass of hydrogen peroxide, and you drank both, it would be obvious to you. It would be viscerally obvious to you that they are not the same thing. The only difference here, they're not made of different elements. Only difference is their ratio. So the ratio as much determines what the compound is as what elements it is. So pure substances can be compounds or elements. And if they're compounds, the ratio also determines what that compound is. But what about mixtures over here?
Solutions.
Okay, solutions are a kind of mixture. We'll put that down here. Do you remember, this is from your vocab, what are the 2 broad categories of mixtures? And there's lots of different ways to categorize something, but what are the broad categories of mixture? Homogeneous and heterogeneous. The very, very easy, even if it seems taboo way to remember this, is homo means same, hetero means opposite. A homosexual is someone who likes the same sex. A heterosexual is someone who likes the opposite sex or the different sex. Homo means same, hetero means different. Homogeneous mixtures seem to be the same throughout. That is, back to our observable universe, our human empirical senses can't differentiate between the components of a homogeneous solution. Homogeneous means it looks the same throughout. Heterogeneous means it looks different. There are different. You can identify different chunks. So give me an example. Someone said that a homogeneous mixture is a solution. A solution is another word for a homogeneous mixture. Those 2 words, that they're synonyms. They don't mean, again, in the strictest sense, they don't mean the exact same thing, but they are synonyms. A solution is a homogeneous mixture, and homogeneous mixtures are solutions. Can you give me an example of a homogeneous solution? Yeah. I don't anymore, but if you have some tea, you usually, there's some gray area, but you can't tell, you can't be like, oh, I'm going to take the tea out of the water. Could you remove the tea from the water? Sure, you could boil the water off, and that's actually one of our definitions of a mixture, is that the components, you know what the word components means, right?
Components can be separated.
Yeah, the components can be separated, be careful though, not just any old way, physically. We can use some physical means. That is, we can, without changing what they are, without changing that it's water and tea, we could separate them. We could boil the water, it's still water, right? A phase change is a physical change. We can boil the water off and be left with just tea, and that would have separated the mixture, right? They can be separated by physical means. Now, what if the tea was made with loose leaf, for instance, if it's got like actual leaves in it? That's now a heterogeneous. Could I go through and pick out the leaves? Yeah, I can see them separately. I can pick them out. So let's get a better example of a heterogeneous mixture, though. Excuse me.
Oil and water.
Sure. If we mix together oil and water, you could tell what was the oil and you could tell what was the water. You could see the difference between them. You could feel the difference between them. You could separate them physically by what? What could you do to separate oil and water?
Oil and water.
You could. It would depend on what kind of oil you use, because some oil might have a lower boiling point than water. Yeah.
Do you have to like use a net to pull out?
Yeah, you could skim it off the top, basically. You might not get all of it, but you could start by skimming it off the top. Sure. Another thing you do, a lot of times oil has a really low freezing point. You could get the water really cold, and that would solidify the oil, and you could just pick it up. So oil and water would be an example of a heterogeneous mixture. You can tell the difference. You can physically see the different components. Whereas in a homogeneous mixture, you can't tell them apart, but they can still be separated physically. A heterogeneous mixture can be separated physically too. It's just that you can tell them apart. So in mixtures, they can be separated physically. Compounds, though, can only be separated chemically. I keep using those words incorrectly. A chemical change is one that will cause the compounds to change. So for instance, if I had a piece of paper, which I did for here's one. If I burnt this, would it still be paper? Would the things that are making up this paper now be the same? No. No, in fact, I'll give you a chemical change example. The paper, C6H12O6 cellulose, would combine with the oxygen in the air to produce carbon dioxide and water. Are carbon dioxide and water the same thing as cellulose and oxygen? No, they're not. They're chemically different, so this is a chemical change. Is it still cellulose? If I rip it, yeah, so what kind of change is that then? A physical change. If I rip it, it's a physical change, but if I burn it, it's a chemical change. Now, are ripping and burning the only examples of physical and chemical changes respectively? No, of course not, but they are examples. If the check is, if it's the same stuff before and after, it's a physical change. If it's different compounds before and after, it's a chemical change. So if I boil water, is that a chemical or a physical change? Physical. It's still water, right? It's water vapor, but it's still H2O. If I mix together hydrogen peroxide and water, is that a physical or a chemical change? Physical. They're just mixed, right? They're just mixed. It's just a physical mixture. Now, back to our discussion of the atom, atomic. What it means for something to be atomic is that it can't be cut. Do you have questions about these basic forms of matter, the mixtures and pure substances, the kind of the basic definition? I wish I would have said that. Basic definitions of matter. Okay, I'm going to erase that then because we're going to start talking about the atom a little bit more, and I want to spend more time on the atom. I'm going to ask you to help me diagram an atom. And as I said before, this whole topic should be a review from physical science, so I don't think you should have any problem with this. If I'm going to draw my proton in orange in my diagram of an atom here, where should I put it? You should know its actual name. Where's the proton's home? In the nucleus. So I have a little positive proton there. Okay? If I insist upon drawing my neutron in purple, where will I put that one? In the nucleus. They're just going to hang out together like that. And if I want to make my electron, I guess, yellow, good luck, viewers, where will I put that? In the nucleus too? You're just going to say nucleus for all of them? No, where's that one go? It's outside the nucleus in the electron cloud. So we have this area here where electrons are likely to exist, and the electron will exist somewhere in there. It kind of pops in and out of existence. It actually, it behaves as a waveform in space-time, and the peak of that wave is a manifestation of an electron. That's a little bit above your pay grade for now. We'll talk more about that in Chapter 5. But the electron exists outside the nucleus. Which of these two particles have mass? I'm sorry, which of these three particles have mass? Yeah, the nucleons have mass. The ones in the nucleus. These ones are nucleons. They exist in the nucleus, and they have mass. We say they each have a mass of 1 AMU, and that's approximate. I believe a proton weighs a little bit more than a neutron. I can't remember, but it doesn't really matter. They're both approximately 1. And does the electron have mass? No, but it's so little. It's 1/1820th of the mass of a AMU, of a proton or a neutron. So it's very, 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 very small. We would need, even to make it round up to 1, we would need 911 electrons, and none of these have 911 electrons. So we say, no, the electron doesn't have mass. We round it down to 0 every time, okay? What have I drawn? Does anyone know what isotope I've drawn? How many protons? Hydrogen. Hydrogen. That's right. The number of protons is hydrogen. Now it has one proton, so it must be hydrogen. And then do you remember how we number it? It's going to be a number here. What is this number? Say it. Mass. The atomic mass. So if it's hydrogen, has one proton, which makes it hydrogen. But what's its actual atomic mass? 2. Because the nucleons have mass, and there are 2 of them. So hydrogen 2. We also write that as hydrogen with a little 2 in the upper left corner. Upper left corner. Hydrogen 2. Review. Yeah, you remember this? I've posted on the Google Classroom already videos from last year's chemistry class that go into a little bit more depth. But the truth is, this is a review from physical science. I don't mean to hurt your feelings by saying you should remember this, but you evidently also do. Every time I ask a question, someone knows it, so it should be a review. One of the things that will be expected of you as actual pieces of work to do on your test is to say, I'm going to give you some isotopes, and you will tell me how many protons, neutrons, and electrons are in it, right? So let's practice that real quick. Let's say we have gallium-70. So we'll be able to read it like this. First of all, we pronounce that gallium-70. And let's say we also have tungsten-182. How many protons in the gallium-70?
31.
How do you know? You're right. How do you know?
Right there.
And what? Yeah. You're not wrong, but how do you know? What says it right where?
It's atomic number.
Yeah, gallium is atomic number 31, meaning that every atom in the universe that has 31 protons we would call gallium, and every atom that we would call gallium has 31 protons. So it always has 31 protons. This, the fact that it's gallium, means it must have 31 protons. How many neutrons? Not fate. You're doing faces like you're doing math, and the answer correctly is 39. What math did you have to do, Will?
Subtraction.
Subtraction. You took, tell me the numbers you subtracted, and then the viewers at home will get how you did it.
I took 70 from the gallium.
Which is what's its atomic mass.
Subtracted it from the 31.
Right, because if the atomic mass is the nucleons added together, and we know it has a certain number of protons, only these two have mass, and so subtracting the number of protons from the atomic mass gives us the number of neutrons, which is 39. What about electrons?
31 to make it even.
Yep, 31 to make it even. You almost sound bored. You know how to do this. It has to equal the number of protons because that's one of the definitions of atom, right? The definition was cannot be cut, but the way we use the atom nowadays means it's also electrically neutral. The positive charge must equal the negative charge. By the way, like charges do what? This is on the test, is why I bring it up. Like charges repel, and dissimilar charges, unlike charges, attract. Opposites attract. Like charges repel. You should probably write that down. I did too. Okay, now tungsten 182. How many protons in tungsten 182?
81.
81. How'd you get that?
Atomic number.
Tungsten's atomic number is 81. How many neutrons then, Wes? Oh, you'll like this, Fate. The reason tungsten...
Oh, wait.
But Fate! You betrayed me.
I was looking at
Made a liar out of me on YouTube. What's actually tungsten's atomic number?
74.
74. Fate was confused because of, also, Fate will love this, the symbol for tungsten is W because the German word for tungsten is Wolfram, and so, the chemists love for things to be international. And at some chemistry convention in the International Union of Pure and Applied Chemistry, IUPAC, the German scientists wanted it to be called Wolfram, the English scientists wanted it to be called tungsten, and the compromise was that it would be called tungsten but have symbol W to stand for the German Wolfram. Anyway, 74 number of protons.
Would it be 32? It's 20. No. Is that 102 or 180?
182.
I thought it was 102.
182. I'm sorry. I made the lid of my 8 pretty small. 182. right?
108.
Wrong. There we go. How many electrons? Let's pretend I made it like this. Let's pretend it was tungsten 182 with a +4 charge. Now how many electrons?
78.
Nope.
70.
70. It must have 4 more protons. That's why it has a +4 charge. We can't change the number of protons, so it must have 4 fewer electrons, 70. I think you're good on that. Now, the final thing that we're going to talk about, you know the charge and location and mass of the subatomic particles, but one of the ways that an atom, even though it means cannot be separated, cannot be cut without being destroyed, all that stuff kind of orbits the Greek meaning of atomos. It is a reality that sometimes atoms do fall apart. What do we call that process? Does anyone remember? Radioactivity. Radioactivity. And there are 6 kinds of nuclear radiation that we talk about. I want you just for now just to list them, and then we will talk about them in a second. Matter, and one property of matter is radioactivity. List me the 6 types of nuclear radiation.
Alpha.
Alpha.
Beta.
Beta plus.
Gamma.
Beta minus. Gamma. Electron capture. And spontaneous fission. And the point of this is that some isotopes, that is some atoms with a certain number of neutrons, tungsten 182 is an isotope, but some isotopes are inherently unstable and so they fall apart. And that process is called radioactivity. And these are the 6 ways, the modes, right? The 6 ways or modes that can happen. Each of them has a symbol. The symbol for alpha is the Greek lowercase alpha. The symbol for beta plus is the Greek letter beta with a plus sign as a superscript. Beta minus is the same but with a minus sign. Gamma is the lowercase gamma. Electron capture is the lowercase epsilon. And spontaneous fission is just the Latin letters SF for spontaneous fission. Those are the symbols. I've done a yucky job with this table. Please forgive me. There we go. There we go. These are going to look nicer. These are going to look nicer. They do look nicer. For each of them, we discuss its mass and its charge. And now, other than electron capture and spontaneous fission, these 4 are leaving the nucleus. So in each of these cases, we're going to subtract its mass from the atomic mass of the parent isotope and subtract its charge, if it has one. We're going to change the atomic number based on that. The mass of the alpha is 4. For what? Every number needs a unit in science. What unit is implied here? AMU. Beta has a mass of none. Beta has a mass of none. Gamma has a mass of none. Electron capture has a mass of none. And spontaneous fission doesn't really apply. Spontaneous fission is when it falls apart into 2 different isotopes. And it's kind of at random. So this one, you're not going to do work with this one. The charge of alpha is 2 plus. Beta plus, can you guess what charge it would have? What kind of charge is beta plus going to have? A plus charge. It's 1 plus. What about beta minus? 1 minus. Gamma has no charge. Electron capture is 1 minus, but we actually add this instead of subtracting it. And again, spontaneous fission, we're not going to do work with that. We will do practice problems with these. There are some on your chapter review. There's a worksheet if you want it, but it's optional because, as I said before, this should be review. Bye.